camera or unmute myself.
Welcome, everyone. I'm extremely excited to have the privilege to introduce to you Denis Newman-Griffis, who is a close colleague of mine. We both consult for the National Institute of Health. I met Denis in 2018 in, now I can't remember where in Australia it was. Melbourne. In Melbourne, where ACL was. He came right up to me after I talked and we started talking, and that's when we started collaborating. He's been a great addition to my research team. Some of my students are here and they maybe only have seen him on Zoom. Here he is in 3D. So
full height and all.
I want to acknowledge that Denis, I've always known that Denis was great, but now there's even more evidence of such because he got the American Medical Informatics Association's 2021 Doctoral Dissertation Award. He is a National Library of Medicine postdoctoral fellow in the Department of Medical Informatics at the University of Pittsburgh. And he, you know, it's very interesting. I met him when he was a PhD student, but if you saw him among my NIH colleagues, you never would have known he was a student because he gained so much respect from all of the colleagues on our team. They really defer to him. And I think that you'll see as he's giving his talk, how much wisdom and maturity of insight into language technologies he has. So I hope you'll give him your attention, and I'll turn it over to Denis.
Well, thank you for that. Thank you for that wonderful introduction. Now I have to actually live up to it. Can folks hear me all right, or should I turn on the mic? Folks in the back? Okay, awesome. So I'll just stick with projecting then. So again, thank you very much for having me. I'm really delighted to be here. I've had a lot of pleasure in meeting and collaborating with folks here in LTI and elsewhere in SCS over the last few years. And I'm really thrilled to get to be here today to talk about some of these kinds of interesting challenges in navigating this trade-off between knowledge and data in NLP in the medical domain. So let's get my clicker actually working. There we go. And so I want to frame my talk today through the lens of a vision paper that I had in NACL earlier this year about kind of the shape of the NLP research, the overall NLP research landscape. And in a lot of AI research, including in our field, basic science, methodology development, data set development, and applied science they tend to be viewed as almost entirely separate. So there's separate publication venues. There's not that much cross-communication between communities, and there's a real lack of shared knowledge of where we stand as a field. But this model is a bit misleading. So there's actually this common substrate of translational research questions that tie together basic and applied science in NLP, as in many other fields. And so translational research is asking things about, how do we bring these technologies to work with real world language? How do we generalize and adapt? And what does it mean to be successful? How do we evaluate the impact that our technologies are having and how we're doing it processing language? So these questions, they enable knowledge transfer of new innovations from basic science into applications, but they also open up new areas and new challenges for us to pursue in basic science research. And so the starting point for this talk is really sitting in this translational space and asking, what are the major challenges that we run into when we try to bring medical NLP systems out of the lab and into the real world? And what can we do and what can we draw on to address these challenges? And what kinds of research do we still need to be doing? So what I'll be doing in the rest of this talk is looking at these questions through two lenses. In the first half, I'll look at the process of medical concept extraction, where we take a text like this. This is an excerpt of a clinical note, which maybe my pointer is working. There we go. And we not only find where we have pieces of medical information that are mentioned in this text, but we also then identify what specific things, what diseases, what symptoms, what medications, et cetera, we're actually seeing, so that we can use these for things like diagnosis prediction or predicting rehospitalization risk or any number of other kinds of downstream applications. And so this process of concept extraction is one of the basic building blocks of many medical NLP systems. And when you have a domain like this, where specificity and precise information is really important, that gets reflected then in how we analyze the language. We're being able to kind of get this really concrete semantic grounding. These are the units of analysis that you want to work with when you're trying to understand what this language is saying and what we can do with it. And so this is an area where we have, there's been a lot of work on this over the decades. There's about 40 years of clinical NLP to draw on here. And there's a lot of things that have been developed. So we have knowledge representation resources. We have, I'll go into some of these, we've got knowledge graphs, we've got terminologies, we've got ontological resources. We've got lots of data sets that have been developed. Well, lots within a specialized domain. It's not really lots compared to things that we have from web data. We've got actually off-the-shelf software that's been developed. So if you want to do medical concept extraction on any particular piece of text, you can go and get one of several different software packages and just run it. And it'll do this process for you. And of course, we've got loads of big deep neural models that are doing these, giving us the power to handle these tasks with a great deal of precision. But there's still this kind of fundamental disconnect between the way that we're building and evaluating these systems and the way that we actually want to use them in practice. So, in the lab setting where we have nice controlled data sets, we can get performance numbers like these. So this is from a recent paper on medical concept linking. The actual data sets and the models and such don't really matter here. What matters is a lot of these numbers are over 90%, which suggests that we're doing this really well. Except when you actually take these, take any of these kind of concept linking technologies and use them in practice, you get things like this, where pagination is getting linked to, this is a hospital PA system. And I've got loads of other examples I could give you. I think one of my favorite other ones was the word bed getting flagged as Bornholm eye disease. And so, when we see this coming up, and these are real examples from work that I've done, it really asks the question of how do we make sure that the medical NLP systems that we're building, that research teams are using in clinical care, these systems are being deployed for clinical research, for clinical care. Big companies, startups have a lot of investment in making these things work. How do we, as a field, make sure that these things are working the way that they're advertised to? And so in the second half of the talk, then I'll take you to kind of the other side of this, to the Wild West of medical NLP, where we don't have any of those resources that I just talked through. And this is an area that I've really helped to get established of NLP for analyzing information about functioning and disability. And this is motivated by work that I've done and that Carolyn is now also doing with the NIH Clinical Center and the US Social Security Administration on tackling this kind of classic problem of information overload, but in this very new and kind of uncharacterized kind of information. And so the general process here is, when somebody applies to Social Security for disability benefits, there's a whole multi-step process that happens. And a big part of that process is that SSA will go out and get all of your kind of recent medical records. And this is going to be often hundreds or thousands of pages of records, and they need to process this information in realistically a few hours. So there's a massive problem of information overload that's completed, or that's created rather, and a real opportunity for NLP to help with making a difference in this process. But what you want out of this information is not just this person's diagnoses and medications and history and so on. There's also this really important information about what their daily functioning looks like, what their experience of kind of their lived experience of their health, difficulties that they're having in their environments. This is the information that really goes into kind of how we conceptualize and understand the experience of disability. And so this has kind of started from this very specific motivation of working with SSA on this particular project, but it's opened up this whole area of research on how do we build NLP technologies to capture information that is looking like this, where we have these kind of long, complex spans. It's got kind of hierarchical structure we can analyze it. And I'll come back to kind of talking through some of the structure of this in a little bit more detail later. But Sorry, I'm getting a little lost. What we don't have, again, we don't have knowledge resources to draw on in doing this. What we do have is modern machine learning techniques, where we can take a deep understanding of what these data look like, knowing the kind of application that we're targeting, knowing what we're seeing and kind of how the structure looks. We can pair that with well-curated data, and we can start to make, in a way that we couldn't 40 years ago, we can start to make viable NLP technologies to perform this task. And so in both of these cases, the medical concept extraction and NLP for functioning, what we have is this interplay between three different things. Sources and representations of knowledge that are in the target domain. So knowing these are things that people who are in this community share with one another. This is kind of a common base of knowledge. Pairing that then with data that capture the phenomena that we're interested in. And this is not a hard sell to a machine learning community. But these phenomena are often endemic to a particular community, and they tend to be quite complex. And so it's important to find the right kind of data that's able to represent that information. And then the third part of this triangle then is pairing these together with a deep understanding of what it is that we're working with. What's the process that we're working as part of? And what do the language and the information that we're targeting look like in practice? And of course, the balance between these is always going to vary. So sometimes we have a lot of knowledge and it's really hard to get data for a specific kind of case. Sometimes we have very little knowledge and we can use some kind of well-chosen data to make up for that deficit, together with an understanding of what we're looking at, and maybe even actually to help build up the knowledge. But it's how these three interact that characterizes how we build NLP approaches for working with specialized language. And just to give you a kind of sneak preview of the rest of the talk, I'll be discussing some examples of how these interact in practical development of both models and processes. So how, in cases where we have rich knowledge for a task, we can take neural models to represent that knowledge and then integrate in new signal from nuanced data. And don't worry, I'll actually talk through these in a little bit. And then how, when we lack knowledge, like in the functional status domain, we can use machine learning guided by a deep understanding of the data to build something that works and could help us to get that knowledge. And finally, then, how knowledge-driven and data-driven approaches can be combined to solve different sub-problems and make NLP pipelines that are much more than just the sum of the parts. So before going into that, I have a brief digression for some definitions. I've used the words knowledge and understanding in a way that I have a specific meaning in mind, and they probably mean different things to you. So when I talk about knowledge, what I'm referring to is structured and computer readable resources that represent information within a specific domain. In the medical sphere, there's a lot of these resources to draw on, but one of the really big ones is the Unified Medical Language System, or the UMLS. This is developed and maintained by the National Library of Medicine. It's part of the NIH. And what it does is it brings together over 200 different expert-developed biomedical vocabularies, links them all together into one resource over about 25 different languages. And it's meant to serve as this kind of computer-readable way of representing the medical expertise that doctors are trained with, so that we can take that and make use of it computationally. And the UMLS combines elements of a number of different things. So it includes some aspects of ontology to identify and categorize different types of things and organize them also into like taxonomic hierarchies. So we know that prostate cancer is a type of cancer. So are melanomas. There are various different subtypes of melanomas. So we can get this kind of tree structure of representing the knowledge. These then are paired with terminologies, which capture what language looks like in practice. So you've got the surface forms and the synonyms that you can use to refer to these concepts. And you see here, these can be pretty different. So we have these examples of hyperlipidemia, elevated lipids in blood, hypolipemia. All of these are referring to the same concept, this code that's over here on the left. And there are even more extreme examples out there where there's zero lexical overlap between these, and you have to deal with multi-word expressions and so on. And so these resources let us be able to say, all of these things, when we see them in text, these are referring to the same underlying concept. And then the third aspect is knowledge graphs, which will be familiar to many of you. So this is recording known relationships between concepts so that you can make these kinds of logical walks. So connecting things like a disease to its effects. So saying that glycogen storage disease has this manifestation of hyperlipidemia, and hyperlipidemia can be treated by things like linolenic acid. And so having this kind of rich knowledge representation and having this fine granularity for representing information is invaluable for things like automated decision support, where we can then build systems where if we run an NLP system and we see that there are indications of consistently elevated cholesterol, we may be able to identify, okay, this may be indicating hyperlipidemia. We know hyperlipidemia can be treated by linolenic acid, so let's recommend that the doctor prescribe linolenic acid to this. So that's the knowledge side of things. When it comes to understanding, this is ironically much more nebulous. And what I'm thinking of when I say understanding is knowing what you're looking for and knowing what it looks like. So what are the processes that create and affect the information that you're looking for? And how is that information reflected and realized in natural language? Take a look at this in practice. I've got these couple of examples from two different medical domains, medications and functional status. And you can see, in the medication examples, there's highly specialized language going on. So this 1 mg IV Versed and 75 mcg IV fentanyl, these might as well be Klingon if you have not, spent a lot of time in the medical domain. But we can take these things and we can break them down into common data elements. So to say that there are dosages that are being represented, 1 milligram, 75 micrograms, 150 milligrams in the bottom. There is a method of administration that's being stated. There's a particular drug that's represented. So we can kind of break this down into different components. If we look then at functional status, this is much more of kind of everyday language. And it's a lot harder to be able to do that sort of breakdown into what are the pieces here. So we can start to do this, to kind of go through this process for these domains to understand what is the language that we're looking for going to look like. So saying that for medications, the vocabulary that we're looking for, we've got brand names, we've got generics, we've got biochemistry, we've got kind of what they're going to do biologically. And we have resources that are cataloging these things. So we can draw on something like RxNorm or Drug Bank or resources from the FDA that give us a good resource for these are terms that we know are important and what they may be linked to. Then in terms of what we can expect in terms of where the information will be and how it will be talked about, we can think about, well, this is going to be discussed by pharmacists, going to be discussed by clinicians, probably by home caretakers. It's mostly going to occur in the context of clinical notes. So we can kind of build our models with an expectation that we're going to be dealing with clinical language primarily. And we can break it down into these nice, well-defined pieces of drug dose, frequency, mode of administration, et cetera. And this is not to say that the medication problem is solved, because it most certainly is not. But we're able to lay out these characteristics and get a good picture of what is the language going to look like before we've started to build any system to deal with it. And we can then go through the same process for functional status and see how different it is, where here we're dealing with everyday words and phrases. We got basically bupkis out there when it comes to resources to actually represent these things a priori. When it comes to who's talking about it and where is it going to appear, now we have a much more diverse audience. So it's clinicians, certainly physical therapists, occupational therapists, but you're also going to get this information from patients themselves, from family members, from caretakers. And so you're going to see this appearing in clinical language, but also in patient language and patient narratives and social media posts. So you now have to deal with a much greater heterogeneity of language. And then again, we can try to do some of the structural analysis, and I'll come back to this later. So we can break down some of these pieces, but there's the kind of elements that go into this information are a lot harder to define cleanly. So we have this kind of much messier state to begin from when trying to build NLP technologies for this domain. So getting this kind of picture and getting these kind of guidelines of what are my data going to look like, why am I getting them, how am I getting them, this is what I mean by understanding, and this is how we can help to set the initial parameters and set the priors for the way that we build our NLP systems. So before I dive into the medical concept extraction case, any questions about that setup, the initial setup? I'm going to pause for questions just a couple times while I'm going through. Chat. Cool. So not hearing any, let's go ahead and dive into medical concept extraction. And this, again, is an area where we have significant knowledge resources to draw on. We have data sets, we have complex and high-performing modeling strategies, we've got off-the-shelf software, but we still have this disconnect between how does it work in the lab and how does it work in the real world. So we can think about concept extraction from text as following this general kind of three-phase pipeline, which will be familiar to folks who've worked in entity linking. And the first stage here is going to be recognizing where are these things mentioned? Where are the mentions of concepts? So here finding elevated cholesterol, ASHD, hypertension in this example. And this is basically NER. This is named entity recognition with a different understanding of what a named entity is. So you're not looking for things that are in the world, you're looking for more kind of abstract concepts, but it's still a fairly controlled set, and you can ground them quite reasonably. In the next phase, we then want to identify candidate meanings. So this is often referred to as candidate generation. So here we're looking at hyperlipidemia, and we know that this could be, well, it could be a couple of different findings, could be a couple of different test results. And we're relying here on knowledge resources, which, knowledge bases, knowledge graphs, which may have very large sets of concepts to draw on that we really want to be able to narrow down for this particular case. And then the final step, once we've got the set of candidate concepts, is choose the best one. So this is normalization. This is the final step of the process. And so here we're going to say hyperlipidemia in this case is this particular finding, or pardon me, elevated cholesterol in this case is this particular finding. So this is related towards sense disambiguation. It's sometimes called biomedical WSD. It's actually a slightly broader problem because it includes aspects of dealing with ambiguity, but also things like co-reference and kind of standardization of language and a number of other challenges that intersect with it. So I want to talk about three ways in which we see this kind of balance between knowledge, data, and understanding playing out in this use case of concept extraction. And I'll start with knowledge-first approaches to a decision support application for emergency department triage. So very concrete use case where we're building NLP technologies. Then I'll bring more data into the picture with looking at some hybrid approaches to normalization, combining knowledge-driven and data-driven methods. And then seeing how pipelined approaches to combine these methods at different stages of a process can improve the overall efficacy of NLP systems. So we'll start in the most fun place to start, the emergency department. So when a patient comes in to the ED, there's a set sequence of things that happens. They are first screened by an ED nurse who will do some quick triage to assign patient priority. You may have 3 priority classes here, you may have 5, it depends on the different department, but you're always going to have this kind of prioritization, and there are set criteria for how you do this prioritization. So once a patient has been triaged, then after an appropriate amount of time, they're seen by an ER physician. They get their diagnosis, they're given treatments for whatever's going on, et cetera. And this triage step, as you might imagine, is really important for making sure that good health outcomes are actually achieved in the emergency department. And one of the common problems that crops up in EDs is acute coronary syndrome, which is heart attacks and other related issues. And this is fairly obviously highly time sensitive, but it's hard to identify reliably. So there's only 40 to 50% of these cases are consistently identified at triage time. And we can assess for ACS based on specific symptoms. And those symptoms will often get recorded during the triage process in free text. So this is a place where we can bring NLP to kind of fit nicely into this overall workflow and maybe start to help improve this particular aspect of the process that has very high impact on patient health. This work is under preparation for manuscript, so I'll skip over some of the details of how exactly this works. But I can show you this example here. So, this is going to be a kind of an approximation that I wrote of a triage note. We're going to get things like patient denies chest pain currently, had chest pain yesterday, sharp plus shortness of breath. That's what SOB means. With chills, no dizziness, still feels SOB. So you get this very, very telegraphic block of language. And we want to be able to look at this and say, okay, here are 5 of the symptoms that we know are common indicators for ACS. And we want to see, are these happening right now? So chest pain is not happening right now because we have this first statement, patient denies chest pain. This seems judgmental. This is just how clinical language is written, is saying denies means it's not there. But we do have shortness of breath. So we have this confirmed at the end. So this is the process that we want to be modeling, is take in this note, output, do we have these symptoms? And when we take an off-the-shelf NLP tool and apply it to this task, it works by and large pretty well. So we get here, what we're capturing is cases where patients were exhibiting each of these 5 symptoms that are highly indicative of ACS. And we get high precision, but we also get a lot of false negatives. Except for in the case of fatigue, that has some interesting overlap with kind of everyday language, tired, and that affects precision pretty significantly. So here, the knowledge that we're starting with, kind of taking a priori, we're going to go from a purely knowledge-based approach. This gives us a strong start on this task, and we can capture, for example, shortness of breath quite reliably. But there's still really a need to develop kind of alternative approaches that can combine with this knowledge-based approach to maybe capture some of the nuance in some of the more complex cases for these other symptoms and improve these shortfalls of recall. So to then get a sense of what happens when you combine knowledge and data in this process and what that can look like, I'll turn to the specific challenge of normalization. So here again, what we have is we've identified a mention of a concept. We've identified candidate meanings for it. So this could be the common cold. It could be the sensation of cold. It could be the temperature cold. It could be about, I think, 37 other things in the UMLS. And we need to pick, which of these is the best case. So here, normalizing this as a mention of the common cold. And there's a whole spectrum of strategies for doing this, from very rule-based approaches where we're relying almost entirely on dictionary mapping, all the way through to your favorite deep neural approach where we're dealing with trying to match a mention to one of hundreds of thousands of candidate concepts. And each of these approaches then has different strengths and weaknesses that it brings to bear. So in a recent shared task on medical concept normalization, this was a collaboration with Dr. Rosé's group, we investigated how these different approaches, these kind of more rule-based and more machine learning-based approaches, worked in combination by putting together this sequence of rule-based approaches with a neural model that we built based on comparing embedding representations of the mentions in context to embeddings of the candidate senses to identify what the best match is. And I want to blow this model up a bit because this also reflects, actually, this is built around the idea of putting knowledge in context with data. So here what we're doing is we're starting with neural embedding representations of candidate senses, which we can derive from expert knowledge in the UMLS. So we can take candidate definitions, we can take surface forms that exist for these concepts, run them through a model like BERT, and we get this nice representation of here's what this can look like in language. And that then gives us our expert-driven representation of what this concept looks like. We then run these through a data-driven DNN to transform these embeddings for a specific context. And what comes out is this purely embedding-based model for kind of taking this expert knowledge that we start the problem with and tuning it to this specific context. So intuition-wise, what we're doing is we're taking this kind of rough projection of, let's say we've got this example of patient has cold symptoms. We could map that to common cold, to cold sensation, to cold temperature, but they're all kind of up in a different part of the space. So what we're doing with this system is saying, okay, let's take this, figure out what do these candidates look like for this particular context, and map it such that the common cold looks the most similar to this particular mention. And this ordering of approaches that we looked at, from the strictest rule-based method all the way through to the final machine learning approach, where we used that embedding-based model and compared a mention to every single concept that we had. This yielded a very cumulative solution to this problem. So each step of the process covered more of the data set and provided increasingly small additional bumps in accuracy. So in the first step, we're using direct matching based on the training data alone. And that gets us over half of the data in our evaluation and about 50% of the total accuracy just by itself. The next phase, then, we add in some more kind of strategies for mapping to the UMLS, and we cover about another quarter of the data set, and we get about another 20% of accuracy. And then we bring in our neural models, and we're able to cover the remaining samples and get another few points out. So by kind of stacking these approaches, we're able to cover different subsets of the data. And when we evaluate each of these steps in isolation, then we see this trade-off going on, where as our approaches are able to cover more or at least different subsets of the data, we see these diminishing returns in accuracy. And what this really illustrates is that none of these approaches is best by itself, because we're having this trade-off between coverage and precision. And we're able to get the best results within the system by combining these different strategies with an eye towards what are the different kinds of challenges that are represented in the data set. And then to illustrate another strategy, more of a pipelining strategy for how we can combine knowledge-driven and data-driven approaches, I want to turn briefly to the step that comes before normalization of how we identify the set of candidate meanings in the first place. And one of the major challenges that you run into in practice is just that there are a whole lot of medical concepts out there. So SNOMED CT, which is one of the big clinical vocabularies, has over 400,000 concepts in it. The UMLS writ large has several million. And in a real world setting, you really want to be able to represent as much of this diversity of information as you can. So it creates a bit of a candidate overload issue, where for any given mention, you're going to get out far too many candidates to deal with, or rather you have far too many candidates to look at, and most of them are going to be completely irrelevant to any particular context. So we recently developed, and this was also in collaboration with Dr. Rosé's group, we developed a general purpose approach to help with reducing this candidate overload issue, where as part of the process of identifying a set of candidates, so here we've got these mentions of cold and cough, so symptoms include cold and cough. We're going to run through an entity linking system, something that we can take off the shelf, and will produce for us a set of candidates. And then what we do is perform this course level identification of saying, what kind of information do I think this is? What type of information are we talking about? So here identifying that for cold, we're talking about a disease, and for cough, we're talking about a symptom. So here, what we're taking is this multi-attention model that's based on transformer representations. We're going to run this sample through and just say, what kind of information am I looking at here? You can then use that to narrow down your search space. In this case, we actually solve the issue because we've narrowed down to just the one disease and just the one symptom. In practice, what this will do is take you down from many hundreds of candidates to maybe 5 to 20. And so using this model as part of the candidate generation process, we found significantly and consistently improves overall extraction performance. This is across several of the off-the-shelf toolkits that you can use for medical concept extraction, and 4 of the major benchmark data sets. These are a mix of biomedical literature and clinical notes. And what you're seeing here is the increase in F1 on extracting and normalizing this information just from adding this module into the pipeline. So we implemented this as a fully modular piece that we could then just kind of stick into these existing off-the-shelf pipelines, not change anything else about it. And by bringing this kind of data-driven perspective of what kind of information are we looking at, we're able to make these pipelines perform significantly better. And so this lets us then have that kind of data-driven perspective of how can we capture the nuance of the information that we're looking at, but also keep the benefits of these more knowledge-based pipelines that give you kind of interpretability, accountability, and also modifiability. They're a lot easier to tweak for any given application. And modeling is only half the battle when you're trying to think about real-world language. So both for our machine learning and for system evaluation, we really need to be working with data that represent the full diversity of situations that we want to be able to analyze and practice. So when we're performing concept extraction in the wild, we want to be able to extract all different kinds of medical concepts. But the data sets that we've developed, the data sets that we've been using for concept extraction research, only represent often a small subset of the types of medical information that we want to be able to get to. So you see here in these 4 benchmark data sets, the green cells in this table these are across semantic categories in the UMLS. The green cells are places where we have at least 10 samples of that semantic category. And you see that only one of these data sets actually has broad coverage across, in this case, all of the semantic types that are in the UMLS. And even that one data set, it's 34,000 samples, which is not bad. But if we want to deal with hundreds of thousands of medical concepts, it's not really covering everything that we need. So we also, as part of this project, we created a couple of large-scale and automatically built data sets. One drawn from Wikipedia, where we were able to link over 1 million different medical concept mentions by kind of cross-referencing with other knowledge graphs to walk to the UMLS. And also then in PubMed abstract, so this is biomedical literature, where we were able to link here over 50 million mentions. And here we use distant supervision, where we brought in the expert curated subject headings that are assigned in the PubMed resource. So these are assigned by a combination of knowledge-based tools and then expert curators. And these, using this kind of distant supervision, let us bring in some of that expert knowledge into the process of curating the data in the first place. And these data sets then have coverage over all these different kinds of medical concepts and give us significantly higher volume than anything that we've had before. So we really envision these as helping to serve as foundational resources for advancing medical concept extraction research with an eye towards these kinds of broad coverage applications. And coming back to that understanding piece then, this also reflects on a broader question that I want to touch on of evaluation in concept extraction research, and of whether when we evaluate an NLP system, we're actually measuring all the aspects of the data that we want to be. So in normalizing medical concept mentions, there's been a lot of work on methods for normalization. There's been a lot of work on methods for dealing with ambiguous abbreviations, which are a huge problem in clinical language. But there's kind of this gap in the literature when it comes to broader lexical ambiguity in clinical language. And so in a study earlier this year, we showed that the data sets that we're currently using for this research, for medical concept extraction in clinical settings, they really fail to capture much in the way of actual lexical ambiguity in clinical language. So we looked at the 3 benchmark data sets you can currently get for normalization research in medical data. Got the share corpus, which was used most recently in a 2015 SemEval shared task. The CUI list 2016 corpus, this is a re-annotation of cases that were too challenging for share and were excluded. And then corpus from a normalization shared task in N2C2 2019 a couple of years ago. And these data sets consistently underrepresent ambiguity. So what you're seeing on the left here, and this may actually work, yeah, that works a little bit better. What you're seeing on the left here is that only between about 2 and 14% of the strings in these data sets ever appear as annotated with like different concepts in different places. Whereas if we look on the right, these are a few different strategies getting kind of more permissive as you go left to right for measuring potential for ambiguity when comparing against the UMLS. And we have this very stark difference that there's very, very little ambiguity that we're seeing in the data sets. And there's a whole lot of ambiguity that we'd like to be able to capture. And this really aligns with the intuitions that we have from a couple of decades of applied clinical NLP, where we know that lexical ambiguity is a huge problem. And so what this is saying is that when we're evaluating medical concept extraction systems, we're really not getting a picture of how well they do on ambiguous language. And we may be getting a misleading picture of how good they are overall. We also found that the annotations that are in these data sets also don't carry over between data sets. So here we're looking at strings. This is overlap between a couple of the data sets. So semival versus N2C2, and then Cuilis versus N2C2. And what's in the middle, the 600 and 185, those are the only strings that were shared between these two data sets. And when we then break those out, we see that nearly half of them in the top case and 2/3 of them in the bottom case are annotated with at least one different concept between the two data sets. And half of the time, or rather a third of the time, sorry, excuse me, a third of the time, they're annotated with a completely different set of concepts. So not only is it that we're not capturing ambiguity, we're also, the annotations that we have are giving us very different pictures of what these terms are meaning in practice. And more than raw counts of ambiguity, there are also several distinct phenomena that contribute to how ambiguity emerges in clinical language. And so this is a typology, it's an incomplete typology, reflecting 5 different categories of things that lead to clinical ambiguity. So these are, a mix of lexical semantics things. We have polysemy, so elevated could be elevated in the measurements, it could be physically elevated. We have metonymy, where something like rhythm could be a measurement procedure, or it could be the thing that is measured by that procedure. We have also then kind of knowledge-based issues in terms of how knowledge is represented in the UMLS. So we have issues of specificity where, like, you could annotate with heart failure, or you could annotate with left-sided heart failure, which is a subtype of it. And then also some issues in terms of synonymy and kind of things that really mean the same but have come from different vocabularies, and we see these emerge in the data. And even in the small samples that we had of ambiguous language in these benchmarks, each of these categories appeared across all the data sets. So the evaluation issue then becomes even more nuanced, that we're not just, we need to be handling all of these different types of ambiguity with different strategies in how we do our NLP modeling. So to summarize, medical concept extraction benefits from this kind of multi-pronged approach in all stages of research and development, where we've got these rich knowledge resources for capturing domain semantics and terminology that can really help guide expert systems approaches. We've got then data-driven models that complement these knowledge sources and help to capture more complex and kind of harder to define cases. And we have this understanding of how the data are produced and why, that really helps to guide everything from building systems for very concrete scenarios like emergency department admissions through to evaluating extraction models in terms of the processes that create ambiguity. So before going on to the second half, do folks have questions about the first half? That's a really good question. So I can say that the model that we developed, so the MedType model was, I think we had about 95% accuracy. So it was doing a very good job at separating these out. So I think there's 2 different questions to that. There's one is how good does it have to be? And there's 2 is how granular does it have to be? So we did our analysis at a higher level of granularity. So we had about 20 semantic categories. The full UMLS actually uses also a second level typology that has 127 different categories. And that, as you might imagine, was a whole lot harder to categorize between. And we actually found doing that more granular level, if we were able to do it perfectly, it would have made some additional difference, but not that much. It really wouldn't have changed the system performance all that much. So I think, possibly the answer to that question is finding a level of granularity where you can kind of balance, this is helping us to do the main thing that we need to do, which is get rid of 70 to 80% of the candidates that we've got. But the categories are coarse enough and separate enough that you can do it quite effectively with a pretty simple approach. Any other questions? All right, so let's go on to the second half then. And what I want to do here is shift focus to this new use-inspired area that I've helped to establish of language technologies for function and disability. And this is a place where the knowledge is a lot less well-developed, but we can learn with the machine learning technologies that we have now from small sets of well-curated data. So disability is a societal phenomenon that has both global and increasing impact. The graphs that you're seeing here are years of life lived with disability by age range, comparing 1990 on the left to 2019 on the right. And this increase is only continuing to accelerate. So disability is an area that's long been kind of underserved by AI and data science research. And it's one where AI technologies properly designed and used can have a transformative impact. So one of the ways in which I've been trying to help make this happen is through the use of NLP to analyze and understand the complex combinations of factors that affect disability, that affect people's experiences of functioning as they're described in text. So what we have here on the left is this synthetic bit of clinical language. And what we're wanting to do then is ground the information that's described here to different aspects of a person's function using this model that's shown on the right. This is the International Classification of Functioning Disability and Health, or for people who like to actually say things quickly, it's called the ICF. And the ICF models functioning as, this is the international standard way of doing this, the ICF models functioning as the interaction between all of these different components. So it's not just a person's health condition, it's information about their body functions and body structures. So we have an example of this here on the left in green, talking about the left ankle injury and a limited range of motion. It's also the organized and volitional activities that we all engage in. So walking around, communicating with others, preparing meals, these sorts of things. And we've got an example of that in orange. And also then this kind of higher level of participation in roles in society, things like engaging in work, engaging in religious practice or you know, friendship community and so on. So we've got an example of that here in purple. And all of these things are contextualized by the environments in which we're functioning. So here, you know, this can be things like assistive devices, like the example here in blue of, what did I use, the crutch. But it's also other factors of the physical, the social, and the cultural environment. And it's through the interaction of all of these aspects of a person's experience that functioning and disability emerges. So to give you a bit more of a sense of what this looks like in language, this is an example of a mention of a mobility activity. And we see here these different components. There's a particular action that's being performed. There's a source of assistance that's involved in the performance of this action. We're able to quantify, you know, the observation of this action. And all of these are kind of interacting with one another to create this one piece of information, this one observation of function. And we can further break this down then into this kind of enriched structure where we have the components of the mention at the top, where we can say theoretically, you know, a piece of mobility information we can break down into an action, which is measured by quantification, which is then enabled by a source of assistance. And we can enrich it then with all these various semantic attributes that we have at the bottom. And having this level of representation, developing this level of representation, then gives us the tools to know how to go into designing, developing, and evaluating our NLP systems for analyzing this information in practice. So in collaboration with the NIH Clinical Center, we've been developing this multi-stage pipeline for extracting and categorizing descriptions of physical activities in medical text. Currently, this includes these 3 stages of recognizing where functional activity is described in the extraction stage, identifying the level of performance that's described, what we're referring to here as polarity, and then also mapping it to categorizing the type of activity that's being described in the normalization stage. And I'll focus today on the extraction normalization stages. And so what we're going to start with is we've got some observations that are recorded by a clinician. And this happens after a patient encounter. And what we want to do in the extraction stage is identify where are the spans of text that are referring to different aspects of functioning. So here we have this description of mobility activity. And getting this out is challenging for a few different reasons. The first being, as I mentioned earlier, we don't have any good terminologies or any really kind of knowledge resources to draw on for knowing what this language about function should look like a priori. And this is also semantically and syntactically complex information. And these are long spans, and it's a little hard to define kind of where the boundaries really are and what the structure is of what's being said. So in some ways, what we're dealing with here is a lack of well-developed knowledge, both at the level of the production of the language and of how we can analyze it. So there isn't really well-controlled language that's been developed for people to actually describe functional outcomes, at least yet. So we get these kinds of blurry language, where the example at the top of moderate difficulty in walking in clinic with cane, this is fairly clearly laid out. But we can also get things like at the bottom here, she has a hard time handling pots and pans to make meals at home. And there's a lot of kind of layers of inference that are going on in there. And you know, what's being expressed is this complex interaction between a person and all these different aspects of their environment that's affecting their ability to take care of themselves by preparing meals. And so this also then affects, you know, how we build the NLP, because we don't necessarily know what we're going to be looking for in analyzing this language, because we don't know what it should look like when it's produced. And when it comes to a sequence modeling style of approach for then wanting to extract these spans, what this means is that the standard approaches don't quite work. So we don't really know where this begins and ends very clearly. And it's hard to define what it means to get it right. So does it matter more if you get just the action? Do you need to get like any sort of strict definition of boundaries? And then also, do we want to try to model the kind of long distance connections that are going on across these long complex spans? So this is where our understanding of the application of the data comes into play, where our primary goal is to be able to just find where this information is in the first place. We're putting it in front of humans. So we don't need to have it identified exactly. So what we did was we developed a flexible neural model called HAIR, for highlighting and annotator for ranking exploration, which was an NLP a couple of years ago. And we effectively decoupled the sequence modeling process into these two separate steps of independent token level predictions that are followed then by a conditional rescoring to enforce kind of some notion of sequential continuity, at least at the local level. And more concretely, the system works like this. So in the first step, we run each token in the input text with some embedding-based representation of the context through this core model to get the probability that this token is part of an activity mention. And these can be pretty noisy. So the second step then, we're going to take these output probabilities, run the Viterbi algorithm to kind of identify the best state sequence going through these. And then we backtrace through the transition matrix in Viterbi to estimate these kind of pseudo posteriors, where we're able to get these smoother layers, kind of smoother sequences of probability that better represent kind of localized confidence that we are in one of these activity mentions. And then the third stage is handing you, the user, or me, the user, a configurable binarization threshold to take these things and turn them into actual discrete spans that I as a human would want to use. And as this was a new kind of information and not really straightforward to evaluate, we also then went one step further and we built a platform to be able to compare the output from different features and different modeling strategies for this task, both in terms of their quantitative performance, but also qualitatively, what seems to be the most useful way to do this and to get this information in front of decision makers. So you can see here an example of what this looks like, where we have, this is an annotated note. So the things that are highlighted in bold are what we want to get out. The things that are highlighted in yellow are what the system predicted. You see here, there's a little bit of a biased towards false positives. And the user can then, in this platform, switch between the outputs of different systems and get immediate feedback, both quantitatively and qualitatively. And in our experiments with data sets from NIH, where we had a pretty nice controlled data set, and SSA, Social Security, which was much more heterogeneous data, this approach really achieved its aim of giving us high coverage of the functional descriptors, where what you're seeing here are scores at the token level. When we did this evaluation at the span level, we were able to cover nearly 100% of them to some degree level. But we do see a fair bit of noise coming through as a trade-off for this high coverage. So the data-driven approach can only take us so far when it comes to dealing with this kind of complex language. So what we've set is this strong baseline while also having definite opportunities for more kind of understanding-driven improvement and fine-tuning of how we do this. And then once we extract this information, we then map it in the normalization phase to a standardized representation. Here we're using codes from the ICF. And this allows us to organize it, retrieve it a little bit more effectively. But again, function poses challenges here in the lack of resources that we have. So just to give you an example of this and how the kind of variation in language affects this, these are samples of surface forms for this category of walking, the ICF category D450. I've given you 9 samples here. We had 156 distinct surface forms in the data set. So we have to deal with quite a bit of lexical variation and also syntactic variation in how these things are described. And again, it's not necessarily clear a priori what the appropriate way to model this task is. So we investigated a couple of different paradigms for this, going from basically a data-driven approach in kind of traditional sort of classification, where we say, here's my mention, let me compare it to mentions that I've seen before and tell you which thing it looks most like, or a knowledge-driven approach where we can develop these neural representations of the ICF categories themselves based on the definitions that are provided in the ICF. This is basically the one sort of knowledge that we do have. And then use similarity of a mention to those embeddings to try to decide which thing does this look most like. And we can represent this in a couple of different ways. So for the classification approach, we're using word embedding features. We used BERT-based embeddings to do this. And we can think about, we have this structure of, we know that there's an action within this activity mention, but we haven't actually built technologies to extract it yet. So our extraction only works at the activity mention level. So we can then analyze, well, if we have the technologies that we have now, how well can we do? But then also in what we're calling an oracle approach, if we were to build a technology that could get us out the action, how much would that help us? And then for the candidate selection approach, this again, we're bringing back this same model of comparing the embeddings of the candidate concepts, here now this is ICF categories, to the embedding of a mention in its particular context. And one of the things that we see right away is the limitations of the small amount of knowledge that we have. What you're seeing in this graph is F1 scores on development data. This is without the oracle settings. The numbers are a bit lower. Comparing both static and contextualized embeddings. And this is looking at just doing cosine similarity of the embeddings themselves. So saying, here's my mention, here's my ICF categories. I've only got 13 of them. Tell me which one it's closest to. And that's terrible. It does absolutely awful at this task. We get 8%, 8% macro F1 with the BERT-based approach. But when we bring some measure of data to this, when we bring a little bit of data in how we can take that expert knowledge and project it for this particular context, the static embeddings still don't do very well. But with BERT features, we're able to get this kind of skyrocketing performance up to something that can actually be reasonably useful in practice. And what we see is that these approaches are able to classify both mobility and self-care and domestic life related activities. So these are a lot of the activities of daily living with quite high accuracy. And we do see here that comparing this without oracle versus the with oracle setting, being able to have this richer understanding-driven representation of the information where we could theoretically get out, here's the specific action within the activity mentioned makes a really big difference in our ability to categorize these things effectively. So the functional status domain is really at the frontier of medical NLP. We don't have any of the knowledge resources or the expert systems that have been built up over the decades for other kinds of medical concepts, but we do have modern machine learning and text representation techniques that can help us to make up for a lot of that gap. And one aspect I actually didn't touch on here is how in this kind of newer domain, the data can actually help us to guide expanding and improving the knowledge resources that we have. So we've been able to use some of these embedding-based approaches to do some terminology mining and start to construct resources for representing this domain. And we're actually also piloting some of these technologies with Social Security to start to see how they can be effective within their actual decision-making processes. If you're curious and you want to learn more about this area or get involved in it, which would be great, I want to point you to a workshop series that I'm organizing on AI for function, disability, and health. We're trying to figure out where the next one will be, but it'll probably be in around November of next year. And I'm continuing to lead some community building efforts around this, including we've got a special topic open right now in the journal Frontiers in Digital Health. So if this is something that you'd like to learn more about or get involved in, feel free to reach out to me. Love to see your work in the topic and just love to see work in this area grow. So to summarize, I'll be quick. To summarize what we've talked about today, all of this work has really been investigating different kinds of exchange between these three elements of working with NLP in a specialized domain. So we've got the knowledge that people in that domain have, that they're bringing to the table. We've got the data that we can get to kind of capture the phenomena that we're interested in. And we need to have a deep understanding of the processes that create the data and what the nature of the language will look like in practice. And a couple of final thoughts that I want to leave you with. There's no one right place to start in this triangle. So we can benefit from all of these sources in NLP research and development, but there's always going to be this kind of push and pull between these different sources. And sometimes we'll have more knowledge, sometimes we'll have more data. And the key point then is to keep this interaction and these different sources in mind throughout the process of identifying your needs and designing your system and evaluating it. And this is how we then make substantive progress on these translational NLP problems. So I want to acknowledge this work. None of this work would have happened without a really incredible team of collaborators. I want to thank my colleagues from NIH, Ohio State, Washington University, Pitt, Johns Hopkins, and folks here at CMU. I think I've gotten everybody who was on one of the papers that I discussed. If not, and you're watching this, I apologize. And that does go ahead and conclude my presentation. So thank you very much, and I'll turn it over to you.
I'll start with one. So the functional, evaluating the functional status of the patient, is there ever disagreement in the clinical notes?
Yes. So if you compare across different clinical notes, so any one note is going to be written by typically one practitioner. So you're going to get their perspective at that time. But you may have, functional status, the construct itself can change and will change over time. And it may change from day to day, but also people's perceptions of it will change. And it's both the person themselves, their own perception of their functioning, and the clinician's perception of their functioning. And so you kind of see variation along all of those different axes of what's the person who's experiencing, what's their perception, what's the clinician's perception, and how is it changing over time that contributes to that kind of variation when you try to combine multiple documents.
The experiments that you showed, is there a sense that these metrics are highly correlated to experience of clinicians?
So are you asking about the functional status domain particularly, or just in general?
both for that perspective.
Okay, yeah. So certainly for functional status, people have not actually been using these things yet. That's a really good question. And I think there's been a bit of a gap. And sorry, for folks on the Zoom, the question was, do these metrics of like precision recall and F1 really correlate to the system utility for the clinicians who are working with these systems? And that's something that we haven't really done a great deal of investigation about. And part of that is because, a system level evaluation is involving how is this thing functioning within this broader process. And so the process of like how the observations are made, how the documentation is written, how it's then going to be used, is your decision support system providing something that's useful? It's going to be drawing on various other kinds of data as well. Whereas these kinds of evaluations, the precision recall and F1, they're very honed in on the very specific problem. So there's a gap in terms of what we're measuring in those different approaches. And what I'd say is that, by and large, things that have been useful in clinical practice are built on NLP technologies that are effective under the hood and that are effective in terms of these standard sorts of metrics. But some of it also is things like how easy is it to implement and how efficient is it to run? So there are some of the systems that have been built in like cancer informatics, for example, where they're using things like the CTAKES algorithm off the shelf, which is fairly old as far as systems go. And it's primarily rule-based. There are lots of neural systems that are beating it, but you can implement it quite efficiently. And it's something that's really easy to integrate with other systems. And the kind of noise that comes through is things that either clinicians can control for or later processes in the pipeline can help to control for. So some of it also, you start to bring in these practical concerns of like, how do you implement it and how can you actually use it in practice?
You said that there's quite a diversity on the lexical format. Mm-hmm. So what is your thinking about where this comes from? And actually, do you see kind of, I assume these are all in chronic health record systems, or they use templates now. So do you see a lot of templates?
So yes. So it very much depends on the discipline and it depends on the institution. So everybody's going to have their own customized templates and customized kind of processes around how they use templates. The lexical diversity, I think, is primarily coming from the fact that we have the rehabilitation as a field hasn't really standardized how to describe this language. So everybody's kind of figuring out, we have these constructs. We know ways of measuring these constructs, but how do you actually describe what you're finding? Especially when it comes to something like a person functioning in context, where it's really hard to be able to standardize that. So it's kind of everybody just bringing their own view of like, this is how I'm going to document it, or this is how the patient is saying it, I'm just going to report that verbatim. There are efforts that are ongoing to improve that standardization. So there's work in physical therapy that's being done to develop standardization, like standardization sources. And I think there's a lot of interesting potential to connect some of the NLP work that we've done with those standardization efforts to see kind of how can we start to map some of that lexical diversity back down to more standardized forms.
It's one of the considerations, like readability, because I think some of these things that you showed were pretty unreadable.
Readability for whom is the question.
Patients.
So historically, no, that has not been a concern. It is now. Because there's a regulatory movement towards open access to patient records. And so there's something of an open question right now of how will documentation practices change to make things more accessible to patients who may be now looking at their records. But historically, the things that are written in the EHR have served the purpose of communication between peers, saying this is what was important about this patient, this is what I noticed, this is what I did, this is what you need to know to now make the next decision. So readability there is kind of, you've got clinicians who are coming from a shared background. So they know how to interpret all these ridiculous things that show up.
Do you think this could help improve this?
Yes, I do. And some, some of what we've been looking at is doing some of this, not only terminology mining, but also starting to quantify what kinds of lexical variation are we seeing, and potentially like what is a little harder to measure, but what levels of specificity are we seeing in how this language is being written, and how can that maybe feed back into things like clinical practice guidelines, talking about like, when you observe this, here's kind of some of the aspects that it would be very helpful to have in mind when documenting it. Yes. That is a wonderful question, and thank you for asking that. So the question was kind of, how does privacy figure into all this? And a lot of the answer is that this kind of work tends to be done behind firewalls. So for example, in our work with Social Security, we are building, we're developing and evaluating these methods behind the Social Security firewalls. So we're using the identified data that they have, and the privacy protection is really about like exposure, like minimizing exposure risk outside the team. So there is a legal agreement in place that allows us to access this identified information. And so because the models are being developed behind that firewall and will always live behind that firewall, then it kind of almost obviates that issue. It does mean that we can't share any of the models, which is, I think, a major limitation of the work and a major limitation for open science. And a lot of how, there's really two strategies for how this works in clinical NLP in general. One is, especially if you're building something that is targeted towards actual use, you will build it behind a firewall. You'll maybe take something that people have developed off the shelf using de-identified data, and you'll like tune it using identified data behind a firewall so that you are able to capture everything you're going to see. But the other strategy is then to do automated de-identification. And as you said, automated de-identification can be broken. It is possible, it is always possible to re-identify someone. It's gotten increasingly hard, but there's really this kind of gray area. And the way that we tend to do it as a field right now is saying, as long as we're within the gray area that is provided by the regulation, as long as we're able to say, we have scrubbed out these 18 different kinds of identifiers that are set out by law in HIPAA, in the Privacy Act. It's not actually the same thing. Then we are fine, and we can do some measure of exchange of data. But there is no free movement of clinical data. So there's always data use agreements that are in place that are kind of the backstop for that sort of thing. And there's increasing work on starting to bring in some of the kind of privacy modeling techniques into, how can we make these models more privacy aware? How can we potentially be working with some of that sensitive data, but kind of keep it segregated off in a different part of the model? But that's a really, I'd say, new and emerging area within clinical NLP. So by and large, privacy has been handled at that kind of process perspective.
Other questions? Okay, so here's my final question. What do you think is the missing tool that would enable, like the next great but this is what we really need. What would you say is like the challenge people can take up that could help you with that?
What a great question. So the challenge for those on the call was what's the next big challenge in this direction? What's the next thing that people can really take up to have a big impact? And I'm trying to think of what to point to as a specific thing. Certainly, I think direction-wise, the challenge is starting to turn more of our efforts to this question of broad coverage. That the way that we've been developing and evaluating these systems has been very laser focused on specific types of information, on modeling and extracting information about diseases, especially, but even particular kinds of diseases. So there's a lot of work on like cancer diseases specifically, and there's so much information that's out there, and there's so much potential utility to be gained from using kind of a more holistic picture of the medical information that's available, of the diseases and the symptoms and the social supports, the social support systems and the medications, and like what kinds of treatments are being provided and when and by whom. And actually brings me to another question, which is very relevant to you. And I think that changing our perspective to look more at a broad coverage and a broad diversity of information, and changing the way that we're building our data sets is a really important one. The other direction is time, is being able to understand, time is absolutely central to medicine. How things happen over time is how a lot of medicine is defined. It's not about a state at a particular point, it's about a trajectory, it's about developments in relation to one another. And we have a really hard time modeling time in medical NLP. It's hard enough to model time in structured data, where theoretically you should have good representations of time. But then when you're dealing with the things that are written in the documentation, you add in then this extra layer of like, this is going to be recorded at a time very different from when it was observed, and that may have been some point in the far back of history. And dealing with those, kind of reconciling those two different issues of when was something recorded, when was it about, and being able to then combine that information over the sequence of a patient's care. That, I think, is the really big challenge to making this information more useful and going from the level that we are now of here's one document, I can pull things out of it, to here's an actual patient chart, and I can tell you something about what is going on with this patient, what you should do with them.
Perfect. All right, thanks everyone. And let's give a big hand to Denis.
Thank you all.